not propagating. The diagrams are with these vertical line strips. So the diagrams are just what's in the middle. And as I showed, we have three fields, right? We have like the scalar field, the vector field, and the tensor field. So the way that they are, I will go into the details more in the next lectures, but this line represents the scalar, the dashed one represents the vector, and you see it also in the gravito-magnetic interaction. This is just like similar to what we know from electrodynamics. And the tensor doesn't enter at this order. It enters at higher orders. So that's also what is so nice about using the energy fields, is that you also have a meaning, like you have a meaning, at least at leading order. When you go to high orders, it's a bit lost, but at least at low orders, you have some physical meaning to the different components of the field. So that's also nice. You see the analogy, for example, with the speed spectrum. Okay. This is just to show off new results, some new results that we got that were not there before, which are like once you understand it, it's super intuitive and easy, but the hard work is to understand it. So using the non-minimal couplings that we were able to constrain, that I showed you before, it was straightforward to be able to compute the leading order cubic in spin sector and the leading order quartic in spin sector that contribute at 3.5 and 4pn, as I noted. These are all leading order diagrams, super simple to compute. It's just one Bragg exchange. So the hard work is to compute the multiples. That was the hard work. But once you do that, then you can kind of get these results more or less for free. It's not exactly for free, but very easy and straightforward. And here we have like some higher order PM results that were not there before. All finite size effects, of course. And another result, a sample of result which was not there before. I show you the most complicated sector of the next to leading order spin squared. So spin squared, as I tried to explain, is the part of the interaction that contains the spin of the same object. So either the spin of the same object and not the spin of the object at another point in time, as you can see here, or just the quadrupole which is induced by spin, like the spin squared quadrupole, which is interacting with point masses. So here you see the most difficult part to compute from the next to leading order spin squared interaction. And so that's the most difficult part. It means that it contains, this is the two-loop part. So now what is a two-loop? Every vertex that you see in a diagram, every internal vertex is a loop. Okay, so it's easy to recognize it as a two-loop. A one-loop looks just like, if you cut this diagram in half, that's a one-loop, which we avoided by having energy fields. Basically, it appears at 1pm. And you can easily see there's a structure here. You can analyze the different topologies, and we do that, and we use the knowledge that exists already from QFT. And that's also the advantage of using EFT in this context, that you have all these techniques that were developed for years and decades of how to tackle Feynman diagrams and quantum integrals, which are just the same, basically. So we use all this knowledge and don't have to reinvent the wheel. As people who did this kind of computations in traditional methods, we were mentioning some names like Blanchet and people Lamour, they kind of had to reinvent the wheel because they were not aware of this kind of analogy that could be used to compute all these things.
But it's already beyond the Post-Newtonian, right?
This is what?
This is already beyond the Post-Newtonian.
This
is Post-Minkowski.
No, this is Post-Newtonian. This is not Post-Minkowski.
But you achieve the Newton constant, so it's high order in G.
Yeah, but high order in G doesn't necessarily mean Post-Minkowskian. I mean, if you also require that your velocity is non-relativistic, then it's Post-Newtonian, and that's the case that we require.
The G is compatible with 3 indices.
We require that our system satisfies
originally I think the Post-Newtonian.
But it's true that the form of these diagrams, if you would do Post-Newtonian computation, you would have similar diagrams, like similar looking diagrams that would just represent something else, and they would, you would weigh them differently in terms of what.
Originally, I think the Post-Newtonian means that if you fix a G order and then calculate expansion with respect to V over C. But once it goes beyond the fixed G order, like this is G.
But it's not, that's the thing, Post-Newtonian is not only the orders of G. It's just that I'm specifically showing you the sector with the highest G, so that's maybe why you're kind of confused about Post-Newtonian. But when you go to higher orders, you also still have just one gravitonic exchange, like a good example is that. When you just go to 1pn, okay? You have one correction that you have is just correcting for the fact that your propagator is not actually instantaneous. It's not non-relativistic, it's relativistic. So, like the way we do it is that we put in you have like a quadratic time derivative in the action, actually. And you have to take it in somehow. So we insert it as some kind of a quadratic perturbative vertex on the vector. You see? So there is this correction here. So this will give us just purely V factors. There's no G here. Just V corrections due to the time derivatives. So you have different ways to put in higher velocity. It's not only that, that's one example. Like correction to the propagators, that would be one example. There are correction on the word line couplings. This is the second. I mean, there are many ways. And one other way would be to insert like higher self-gravitational interaction, which would be corresponding to higher G's. And this is like the higher loops that one has to tackle, but that's not the main or only contribution. But yeah, okay.
By the way, another naive question.
Sorry. Yeah.
If once we have loop effect, in some sense, how can I say this is not a quantum gravity?
How do I say that?
Yeah, because once we have loop effect, so how do I say this is not a quantum gravity? Is here the
Yeah, so that's like the super most common question that everybody asks. That's what I was trying to highlight at the beginning, is that always there is this confusion when you try to tell people that we are doing tree-level computation because we are doing classical physics. So please note, there are no loops. As I said, the diagram is with these vertical lines are stripped. So the diagram is only what is inside. So you can look at all the diagrams, there's nothing, there are no loops, right? There are no graviton loops. So there are no loops in H bar. There is no such loop. The loop is, if you choose to look at it in position space or in momentum space, either way you choose, is that you can fix this vertex. If you think about it in position space, it can be anywhere, right? Between the worlds. Or if you think about it, I mean, the way we do the computation is in momentum because it's easier. We have all this knowledge from UFT about momentum integrals. So if you go to momentum space, it's just loops in momentum. So the point is, that's what I was trying to highlight about EFT being so universal as opposed to what people think of it as something which is quantum. Every nonlinear theory is computed with loops. When you compute, I happen to make some computation in large-scale structure. And this is just nonlinear equations, which are classical, fluid equations, not even related to gravity, nothing like that. But the point is that once you have nonlinear equations, and you expand and you try to solve them non-linearly, at the next order you would tackle integrals, which are integrals over, like loop integrals over momentum. So that's a very general feature for every nonlinear theory that you do in every context. Okay, so that's the loops that we have here. It so happens that the loops are in momentum. It's just that in our case, the momentum would be, instead of being the 4 momentum, it would be a 3 momentum. In our case, because we make a separation of time and space. So all of our things would be in D equals 3 instead of D equals 4. That would be the only difference. But all the QFT books that you open and do dimensional regularization, right? You do everything with general D. At the end, you take D instead of B to 4, you take it to 3, and everything is the same. Okay, so that's what makes our life easier. That we have all this knowledge, we only have to make some modifications to it. Okay, I will just mention the code that we put out. We created this code and tried to put all of what I was trying to present to you before into a public code that will do everything from scratch to the most advanced thing that we can do. So we start by I started by presenting the theory. So in the code, we start from going from the theory to the derivation of the actual final rules. Then we have a unit that actually computes, like even all the rules of the game, of the theory, what are all the final graphs that contribute to a certain order. And then these units connect to a main unit that does all the possible manipulations on Feynman integrals that we have in the specific context. Another unit that comes in is providing just general input about what are the master integrals that we have to tackle. As I just said, we need all this information about what are the generic loop integrals that we are tackling. And this is not easy. This is technical, but one should do that. So this is the unit that is about that, about providing the master integrals. And at the moment, it's developed up to 2 loop, and even that is not so efficient. I mean, it could improve it, but it should be extended, of course, as we go to higher precision. And from all these, eventually, we extract an action. And once we extract an action, we don't care about EFT anymore. We don't care about anything I told you before. Once we have an action, we start to play. And we start providing things to LIGO people or gravitational wave people. We start to compute different observables and different quantities that they would be interested in. Motions of motion, Hamiltonians, reduced Hamiltonians, effective one-body Hamiltonians, binding energies, and if you want to work depending on your ferocity, you can get to the amplitude and phase of the final gravitational waveform. We didn't do that, but in principle. So basically, the final unit is about connecting our result to the actual quantities, observable quantities that people are interested in. At the moment, this is the unit which is partial and definitely has room to be developed. I would say infinite room to be developed. To conclude, I'll just recap all the results of the work. So I would say that the important results of the formal work that I presented would be that we provided an EFT for spinning gravitating objects, which was not there before. We provided a complete EFT formulation for spinning gravitating objects. We were able to provide spin-induced non-minimal couplings to all orders in spin, which were already used up to 4 precision, as I showed you. And another consequence of the nice formulation that we provided is that quantities that are very desirable for gravitational wave people, which are just equations of motion and Hamiltonians, in our formulations, they are straightforward to derive. And that was definitely not the case before. They were impossible to derive, actually. Just to go over all the practical results that we achieved. So we derived everything basically from next to leading order north. Next to leading order, spin orbit, spin 1, spin 2, spin squared. Next to leading order, spin 1, spin 2, spin orbit, spin squared. I showed you the leading order, spin cubic and spin quartic that we computed. And finally, we took all this knowledge, we put it in the code, and we published it. And it includes an observables pipeline that should be further developed. We did this year. And just to know that it's an unprecedented situation. It didn't exist before this situation. The spinning and the non-spinning sector are actually in sync in terms of the accuracy. So now it's really the first time that all the sectors, even the complicated spinning sectors, both of them, at the moment, they cover 4 p.m. So that's the state of the art at the moment. And prospective work that for me I find more interesting is, as your question was before, particular, it is interesting to tackle the formal matching of the Wilson coefficients, even if it's not for black holes, it's for the general case. So I'm interested in this, but would be considered as an academic problem at the moment, and I think people would say it's academic at least for the next decade, unfortunately. And also to tackle the radiative sector, because I was telling you that my work focuses on the conservative sector, so to tackle the radiative sector properly, which was not done before, with spin, so to formulate properly in EFT, and then to do all these kind of implementations that we need order by order to cover all the sectors, write the code, whatever, all of this should be done. So this is a lot of work and not done before, and people, there is a need for it, so this would be good to tackle this. And with this I end. Can you tell me if Mandarin appears here? Does Mandarin appear here? Does your language appear here? Yeah? Which one? Tell me. I don't know. Is that? This? Is this your language? No, this? No.
The opposite at the top.
At the top?
Yeah.
This? Ah, so thank you in your language. In every place I go to, they tell me which one is it. So thank you. For me, like this is the same, but yeah. Sorry.
So about the Wilson coefficient for point particles.
Yeah.
You're saying that for black holes C is 1.
Yeah.
Why is that true?
Because you have no UV physics to describe when you have a black hole, right?
So that's
When you have like a star, you have some microphysics going on in the